So chapter 10 is talking about exponentials and logs. We'll learn about logs a little bit later, but logs are the inverse of exponentials. Since we just talked about inverse, logs and exponentials cancel each other out. So again, this first page is not in your notes. So an exponential problem is a graph that looks like long graph. You guys have all heard the term, or probably, where someone says they got exponentially better this year, or they got exponentially worse would be the opposite of that. But when they say exponentially in that term, it just means that it happened, they got a lot better or a lot worse. But the reason for that is exponentially is where it kind of grows a little bit, but all of a sudden it starts getting bigger and bigger and grows faster and faster, and so it gets really steep, or the opposite way. It could be really steep and get slower and slower and slower. So my favorite example of an exponential is multiplying by 2. If you take, any number, we'll start with 2 just to have some consistency. If you take 2 and multiply by 2, you get 4. Not a big deal. 2, you get 8. A little bit bigger. If you get 8 multiplied by 2, you get 16. If you keep doing that, you notice the jumps get bigger and bigger and bigger. And if you match the graph, actually that's what this graph is. If you take 1, 2 times 2 is 4. It gets a little bigger. 4 jumps all the way up to 8. 8 jumps to 16. Well, if you keep that pattern going, eventually you'll get up into like 1,000 times 2 jumps 1 whole thousand. So that's the whole thing. It's kind of like looking at what you're increasing by or decreasing, where it starts smaller, but every time you go, that doubles, and so it gets bigger and bigger. The other example is the opposite way if you cut something in half. If you start with something that's 100 feet long, and you cut it in half, then that's 50. Cut it in half again, that's 25. Well, it gets smaller and smaller and smaller and gets little and little. But again, once you go on, it gets slower and slower. Example, maybe that's not it. But it's not. So there is 2 different things looking at exponentials. Actually, before I say this, one vocab word you need to know is the base number. The base number is the exponent. I'm sure I talked about this before, but the thing that makes it an exponential problem is when the variable is your exponent. It's not that it has an exponent, it's that your variable is an exponent. So if you have x squared, that's not an exponential. It's a quadric. Because it does have an exponent, I get that, but the exponent is 2, not the variable. Your exponent has to be the variable. And then again, the base number is the number that has the exponent with it. So that base number is going to tell you if it's a growth problem or a decay problem. A growth problem is what this one is over here, where it gets bigger and bigger. And if it's a growth problem, we'll talk about this later, but that base number is bigger than 1. Again, you don't have to write that down. We'll talk about it a little bit later. For this one is y is equal to 0. Now in this chapter, we're going to learn about horizontal asymptotes. So this y is equal to 0 is this line right here. Now, what even is an asymptote? That's the other thing I want to talk about. So an asymptote is a line where your function will touch it, but it's going to get very, very, very close to it. So again, if you think about what I said earlier, where you take a piece of wood and you keep cutting it in half, it's actually a better example to start with like 16. 16, cut in half is 8, cut in half is 4, cut in half is 2, cut in half is 1, cut in half is 1/2, cut in half is 0.25. If you keep cutting that in half, you'll never actually get to 0. You'll get really, really close. You'll have 0.0000 something, but you'll never actually get in 0 because everything you'll split a little bit shorter and a little bit shorter. So that's what an asymptote is. Now again, there's vertical asymptotes and horizontal asymptotes. We're only going to deal with horizontal asymptotes. Now again, if you look at this, it's kind of obvious because you can see how this graph gets really close to that line, but it never actually crosses. So that's where that asymptote is going to be. So the other example we have is an exponential decay problem. And this is more like I was talking about earlier, where you keep cutting something in half and it gets smaller and smaller and smaller. If you cut this one in half, it's 4. Cut it in half, it's 2. Cut it in half is 1, 1/2, 0.25. 0.0, I'm not going to be able to get it from there. But it gets closer and closer to 0, so that's why it's decay. Again, notice your base number is smaller than 1 for this one. If it's smaller than 1, it's a decay problem. And again, your asymptote is the same place, that line that it doesn't actually cross. Any quick questions over just like, again, some little vocab words, and again, the growth and decay part, if it's bigger than, talk about that in a little bit more detail in a second. But honestly, maybe the biggest thing is making sure you know the base number is the number that has the exponent. That's your base number. That's what you're looking at for growth and decay. A little bit later, you'll see that we're going to add a couple other numbers that means some other things, but that's the big one you have to look for. Okay, so starting now into your actual notes where you can write some of this stuff down. Exponential growth, exponential decay, exponential function. Your b is your base number. If that b is bigger than 1, it's growth. Decay. Technically, I put this up there. Technically, which means essentially in math terms, it can be negative. If it's negative, it means something else, and we can talk about that a little bit later. But I think it's almost just easier to remember. If it's bigger than 1, it's growth. If it's smaller than 1, it's a decay. If it's negative, it means something else. So label these as growth and decay. Again, this is not rocket surgery. Just look at the graph. As you go from left to your right, just like you read, if it goes up, it's growth. If it goes down, it's decay. So this one goes up, that's growth. That's decay. The next one goes up, it's growth. And the next one looks a little bit strange, but it still goes up, so it is growth. When I give you a graph, that should be the stuff you knock out of the park because, again, even if you had to guess, I think most of you guys would be able to do that just by, again, if you look from your left to your right, it gets bigger and bigger. That's a growth. If it's getting smaller and smaller, it is a decay. From each equation, state the y-intercept and if it is growth or decay. So we're going to talk about, I'm going to have to change that. We'll talk about the y-intercept also in a little bit, but the y-intercept is the number that's out for purposes. That's the y-intercept. I'm going to talk about this a little bit later, but that's where the y-intercept starts. Here, once we get to B, the transformations, we'll start with the y-intercept and move it up and down, left and right. But if I ask for your y-intercept for these problems, for these graphing problems, just that. My y-intercept for this one is 12, and then you look at the base number. It is smaller than 1, so it's decay. Next one, there's the base number, and this is where it gets a little bit tricky. The base number is 2. That is not your y-intercept. If there is no y-intercept, it's always going to be 1. That's always where you start off with. Nothing there. So y-intercept is 1. This is a growth because that number is bigger than 1. By making the y-intercept a fraction, not a huge deal. Don't fall for that. The y-intercept is 0.25, and it's a growth problem because again, it's bigger than 1, so it's growth. And lastly, again, your y-intercept is 1 again, and this one is a decay problem. I will say be careful of fractions because a lot of people, when they see a fraction, they think that, oh, fractions are smaller than 1. This one is smaller than 1, you're right, but sometimes they make where the bigger number is in the numerator, and then that's bigger than 1. So just be careful if you see a fraction, make sure you double check that. And again, that is your y-intercept, the number in front. That's your y-intercept unless you move it up, down, left, and right. We'll talk about that in a little bit. But I will tell you, I'm not going to try to trick you. I'm not going to say like, hey, what's the y-intercept of this? And then you say 12, and I say, well, but then we actually moved it to the left or the right. Actually, that would be a really good bonus question. But I'm not going to just do that. So the y-intercept is what we can keep. Any questions before we move on about the growth or decay and the y-intercept? And again, what I'll probably say a lot is it's the starting y-intercept. It might move from there. And we'll talk about that a little bit because we're going to start graphing some of these. We've done this before with quadratics. We did it with absolute values. We did it with square roots. Or we did transformations. So we moved things up, down, left, and right. And we did stretches and compressions. So for this one, the left to right is the one that's inside your exponent. So if it's up with your exponent, it's left and right. And again, just like before, it seems like it's opposite. So hopefully you vaguely remember x plus 4. That means we actually go to the left 4 units. Up and down is the k. That one does make sense. If it's plus 4, you go up 10, you go down 10. Then in front, we have the stretch or compression. But again, that stretch or compression, for our purposes, I just say it's the y-intercept. And I promise you, and I probably shouldn't give you this information, the transformation, put any stretches or compressions on there. Talk about that with some other functions. For me, the stretch and compression part is going to come when we do the graphing. And like I said, the graphing part, we're just going to keep that as our starting point for our y-intercept. Only other thing, and we don't do this very often, but again, if your A is negative, that actually means it's reflected. So that's what we talked about earlier, where if you do end up with a negative number in front, it's just a reflection across the x-axis. So using that table, and you're not going to get this table on a test to memorize it, which again, most of you guys, it's not going to be hard because we already did a couple chapters or a couple lessons like this. One of the transformations, so number 9, let me make this a little bit. The x plus 4 means we're going to the left. Remember, in the exponent is left and right, and it always seems like it's opposite. Number 10, it is down 6. Not for nothing, but number 9 and 10 are both growth problems because the base number is bigger than 1. You don't have to write that down, but it's good to kind of keep that in the front of your head. Number 11, there's 2 different things. We go to the right 7 and up 2. Again, technically, that's a decay problem. We don't have to worry about that yet. And number 12, left 6, down 10. Don't make those harder than they have to be. And again, up here saying they're like super easy, it's a memorization problem. So let's move on then to some of these graphing problems. And here's how you're going to graph these. This is my hint. You're going to start with, remember when I told you that the y-intercept is just, so number 13, I'm going to say, this is where it's kind of hard for me to figure out how I want to define this, but I'm going to tell you that the y-intercept is 4, but it actually isn't 4 because that's just where we're, or sorry, 1. That's where it's starting, and then we're going to move it up, down, left, and right and do a couple things with it. So again, technically it's not the y-intercept, it's just where we're going to start with the y-intercept. And like I said, I don't know better. Super confusing. The things you should, before you do anything else, figure out what your y-intercept is. So for this one, the 4 is not your y-intercept. That's your base number. That tells you it's a growth. So your y-intercept, it's not listed there, it's just 1. Get closer here so we can all, it's close enough. What I'm going to put down in here, and I don't know if you want to do it as a dotted line. Eventually, if you don't write this line, that's okay. But the other thing you want to be aware of is the asymptote, which always starts at 0. So the y-intercept might be a little bit different where it starts, but the asymptote always starts at 0. So remember, that asymptote, we do not cross that line. We'll get close to it, but we won't cross it. Those are the 2 things I start with. I do the transformation. So this means I go to the left. Then we go down 3. That y-intercept, I go to the left. 1, 2. I go down 1, 2, 3. So if you do the same thing. Now the asymptote is a horizontal line. So if you go left and right, it doesn't actually change anything because it's just a horizontal line. But you definitely have to go up and down. So I still just consider it as just so you don't get, I go to the left 2 and down 3. So left 2, down 2, 3. Now my asymptote is this line right here. Now again, eventually, if you don't want to draw that dotted line in there, you don't have to. I recommend it. I think it makes graphs look a little bit better. So before I do anything else, obviously that's not your graph yet. So far, so good. Are there any questions about how we got to that point? How the asymptote moves down and all that stuff. We always start with that asymptote is always at 0. The y-intercept, where you start, equation, and then you just move your left and right, up and down, those two things. Once you do that, the only other growth or decay problem means it's a growth problem, which means I'm going to start really close to this asymptote, and then I need to cross that new point that used to be my y-intercept, and then it's going to get really big really quickly. Here's the deal. This is just an estimation. Actually, the fact that I went through that other point, just in case that's misleading, to do that. Hold on. Come on. This is just an estimation. So the punchline is, if it's a growth problem, you start really close to your asymptote. Don't cross it, because that'll be half point off if you cross that. Make sure you go through that point, and you move it, and then all you have to do is put it up here like this. You don't have to go you can go a little bit shorter. Just make sure the biggest thing that some students do, they accidentally get carried away. They make it look somewhat like a parabola. Back is to not come back to the left. That technically isn't a function. It wouldn't pass the vertical line test, but neither here nor there. Just background. Technically, it will go to infinity on the right-hand side because it keeps on going up. So let's go to the next one. The next one, the y-intercept starts at 2. And then your asymptote always starts at 0. Then from here, this says you move it 1 to the left, so that y-intercept now moves over here. The asymptote, again, if you move it to the left, it doesn't actually change anything, which is fine. But now we have our starting point. Now, the only other thing is a growth or decay. This one is another growth problem. So it starts really close to that asymptote, crosses your point you're talking about, and then again, it just swoops up. It doesn't have to be super accurate. But I check when I grade this. I check the asymptote. I check that, again, I check that point, and then I check the general shape of your graph. Number 15, do the same thing. This one, again, this is not your y-intercept. That's your base number. That tells you if it's growth or decay. So technically, my y-intercept is 1. So my y-intercept is starting at 1. My asymptote is always 0. From here, we go to the right 3 and up 2. So up 1, 2, to the right 1, 2, 3. So that's my new, where my y-intercept was. But now you do the same thing with your asymptote. I go to the right 3 up 2. So 1, 2, 3, up 1, 2. So that asymptote is right there under that. And now we shape the graph. This one is a decay problem. It is 1/2. It's smaller than 1. So again, it doesn't matter where you start. You start really high, swoop down, make sure you go through that point, and then again, make sure you don't cross that asymptote. You get really, really close, but don't cross it. Technically, if over here you touch it, I'm not super upset. Just make sure you don't cross it. And last but not least, number 16. Again, we start off, my y-intercept is at 2. My asymptote is at 0. This one, you don't go left or right any, but we go down 2. So everything goes down 2. That's my new point. Go down 1, 2 to my asymptote. And again, this one is a decay problem. So it doesn't matter really where you start on the left-hand side, but start really high. Make sure you go through that new point, and then again, get really close to your asymptote without going over. And again, just to make sure it's said, because this one happens more than the last one, A lot of people, when they come down, they go through their point, and then at the very end, they come up a little bit. Just make sure you don't do that. I never know if it's an accident or if you think it's a parabola, but that part where you come up is not going to be the correct thing. That's not an exponential. My computer's going slow. How is that? Any questions on that? Those graphing problems. I will tell you, if one of your questions is, what if it's a negative and what if it's reflected? Again, I mean, not to be that guy, but I'm not going to give you any of those. You might see a graph that looks like that, and you might describe the transformation, maybe, but I'm not going to make you graph one like that because I just think it gets a little bit more complicated. So when I say that, what I actually mean is like problems like number 20. We'll do the domain and range for that one, but I'm not going to make you graph one of those problems. So don't lose sleep over that. So the next thing we're going to do is the range, because you do problem, I'm going to have you do all of it. You'll graph it and do the domain and range. So I thought about whether I should go over this or not, but then I thought we just did a chapter, and honestly, this is a lot easier than that. The first thing, the domain, left and right. So which x values are on this exponential? Well, I know my graph didn't do this, but there's so on the left-hand side, hopefully it's pretty obvious. It goes all the way to negative infinity on the left-hand side. This is where it's harder because it does get really steep. And the conundrum with this, almost a paradox, is that it does get steeper and steeper and steeper as you go, but it's not actually it's never gonna stop. It's gonna slowly creep to infinity. So it goes from negative infinity to, so this is all real numbers. Or you can put all real numbers, however you want to do it. But here's the beauty of it. All of them are like that. Every exponential graph you have is going to be set up that way. That's part of the definition of an exponential. It's always going to go positive infinity, so it's always going to be all real numbers. So the domain, every time you see one of these, is all real numbers. I will do that if I didn't put those on the test because I want you to get some easy. I don't remember if it's multiple choice. I don't remember if it's short answer, but if I ask for the domain and range, part of it is because the domain should be a pretty easy one. Now the range is a little bit different. Now I told you it gets steeper and steeper, but it will slowly creep to infinity. That is not the case the other way around, because remember I told you the asymptote is where it never crosses this line. So it gets really close to that line but doesn't cross. So your range is, you always start with y, and then it's got to be bigger for this one. Bigger than 0. Y is greater than 0. I'll be honest, if you put greater than, I'm going to count you wrong, but I think technically it's just greater than. It's never actually an equal. But the reason it's like that is because it's going up. That asymptote, that green line, it's everything above that, so y is greater than. Moved up here, and again, it's pretty easy to see where your asymptote is. If you ever are confused at all where that is, you can let me know, and I can try to help you out or give you some hints. But hopefully it's pretty clear. So that asymptote is right there at 2. My y is greater than 2, because again, it's above that line. Thing, it goes to infinity, goes to positive infinity, and then as it comes down, it hits all the other numbers until it gets to 2, but it never actually hits 2. Now, this is where that changes a little bit. This one, your asymptote is still right here, so that's at -3. So it's y, and it is -3, but now it's everything below that line, so its y is less than -3. I'll have to ask around, because I assume it's, I can't imagine that the equal two signs would go with that, but I feel strange about it. Do you know whether the, okay, that's what that's what I assume. It just feels weird. Yeah. Okay. go ahead and do number 21 and 22 on your own. This is everything we just did. You'll graph it, and then you'll do the domain and range. But spoiler alert, before you even graph it, you know what the domain is. All right. My two answers are up there if you want to double check work quick. Again, the domain is all real numbers for both of them. For the range, if in doubt, always make it greater than. The only time it's going to be less than is if it opens downward or if it goes downward. And again, especially if I make you graph it, I'm not going to give you any like that. That's one of those on the test. There's going to maybe be one like that, but I basically hopefully you know the difference and you can tell the difference between greater than or less than for those things. But if you aren't sure, if you have to guess, if you're forced to, always do greater than because that's more likely, at least for our purposes. Sorry that number 22 is a little bit off our graph, but not the worst thing that's happened. Any questions on those before we move on? And again, the big thing to realize with these graphs is they are not exact. They are just estimations. The only thing that I check for exactly is where your y-intercept was, or where that point you started is your y-intercept, and the asymptote and the curve, or the shape of it, if it's a right general shape. So last but not least, my favorite part of this lesson, because I think it's the easiest part, what is each type of function? So I have, I guess I could ask which one is exponential. I think maybe that's what I do on your homework check today. But remember, the biggest thing is an exponential one is the one that the variable is the exponent. The variable is the exponent somewhere. And really, I think the hardest part of this is remembering what you called stuff before. So the first one is just linear. That is y is equal to mx plus b. Also, the variable is not an exponent. And there's no squared or to the third or anything fancy like that. Hopefully you kind of are picking up on linear. The next one is a quadratic. It's got an exponent, but the exponent is 2, so it's not exponential. The next one is our exponent. It's got the exponent as your variable. That is maybe spelled wrong, but you can't read my handwriting at the end anyways. And the last one is an absolute value. Oops. I will tell you, if I do this on a test or a quiz, those are probably the only 4 options I will give you. Obviously, there's more than that. We have cubics, we have quartics, we have square roots, we have some other ones. Square root could be fair game, because you guys all know square roots, or you should by now. But I'm going to try not to give you anything outlandish. And then the last part is looking at the graph and telling it. So it's a V shape. This is absolute value. The U shape is a parabola, which is a quadratic. Make sure you tell me it's a quadratic. I'm not asking what the graph, what the shape is. I'm asking what the function is. Parabola is how the shape looks. Next one is linear. And again, hopefully now number 30 you're getting pretty used to is your exponential. But you do need to know basic ones. Again, I don't think I'll throw square root in there, but that would be one that I'd expect you guys would know. If you have any questions, let me know. Oh, we only have 5 minutes. It's a Wednesday. Shoot. Okay.